5.6 is going to work backwards from 5.5. So we're going to be looking at an integration that is actually representing one of our inverse trig functions. So the key thing in this section is being able to recognize that the relationship you're seeing in an integral is one of these key inverse trig relationships. So for example, we know that the derivative of inverse sine is 1 over the square root of 1 minus x squared, which means that the integral would be inverse sine or arc sine of x plus c. Similarly, the derivative of inverse tangent is 1 over 1 plus x squared. So if we have the integral of 1 over 1 plus x squared, this is the same as inverse tangent of x plus c. And lastly, over here for secant. We don't need to worry about the other three inverse functions because we really just need to multiply them by -1, and then we have them. So it's all well and good if you can see an integral that looks exactly like these three integrals here and identify that that is actually one of these inverse trig relationships. But what happens if what's inside the integral, what happens if it almost looks like one of those? For example, what happens if I have something like on number 2? This looks a lot like a tangent relationship, but there's a 4 in front of the x squared and there's a 25. Or this looks a lot like an arc sine relationship, but what's happening on the inside of that radical sign is a little bit different. So that's what we're going to focus on next. We're going to derive how we work with this when it is not exactly the same way that it is set up at the beginning. So this is going to feel a little bit like the last section, but we're going to start with the derivative of inverse sine of u over a. So where a is a scalar and u is the x part, the more complicated part of the function now. Not just x, but 4x or 2x. So we would first, before we even take the derivative, we would set this up as y equals inverse sine of u over a, which means that sine of y equals u over a. So we can set up our triangle. Sine is u. The hypotenuse is, so opposite is u. The hypotenuse is a. So this other side would be the square root of a squared minus u squared. Let's take the derivative of both sides with respect to x, because remember, u is a function of x. So this is going to be cosine of y dy dx. Actually, I'm going to go y prime. I'm already low on space here. So y prime cosine of y equals u prime, because remember, u is a function of x. A is just a scalar, so the a is going to stay the same in the denominator. Now let's solve for y prime. So y prime is going to be u prime over a divided by cosine, which is the same thing as multiplying by secant. So I'm going to say times secant of y. But we can tell what secant of y is based on our triangle up here. Secant of y is going to be the hypotenuse. So this is still u prime over a. But the secant of y is going to be the hypotenuse, which is a, times the adjacent, which is the square root of a squared minus u squared. So the a's are going to cross off, and we're going to get here. So the relationship that you're going to see is if your u squared is, let's say, if u is sort of 2x, then that 2x is going to come into play on the other side when you integrate it. And I'll show you some examples, obviously, of how this works. Let's derive tangent. So I'm going to start with a similar triangle. I'm going to start by saying that y is equal to inverse tangent of u over a, which means that tangent of y equals u over a. And then we're going to take the derivative of both sides with respect to x. That's going to give me y prime. The derivative of tangent is secant squared, equals u prime over a. If I solve for y prime, I would be dividing both sides by secant squared, which is the same thing as multiplying by cosine squared. So cosine squared of x over a. So now let's look at our triangle. We're saying the tangent of y is u over a, so tangent is opposite over adjacent. So this hypotenuse is going to be the square root of a squared plus u squared. So this is going to become u prime still over a. Cosine squared, we're going to get from this, cosine is going to be a over the square root of a squared plus u squared. And we're going to square this. Let's rewrite that so you can read it. So what's going to stay here? U prime is going to stay. I'm going to end up with a squared over a. So one of those a's is going to divide out. And then in the denominator, if I square that square root, I'm going to get a squared plus u squared. So this is coming down to this one right here. So this a, this extra a, is going to end up going into the front. Thinking about it as reversing the chain rule, if I needed an a here, what I would do is I would put an a on the inside and I'd put a 1 over a in front of the integral. So that's why there's a 1 over a in front of this integral. It has to do with reversing the chain rule or using u substitution, and you'll still see it that way. So that is where this arctangent comes from. I'm obviously out of space, so I'm going to encourage you to try the secant one on your own. It follows really similarly. You just have to remember to include the absolute value on that one because of domain. So let's focus on the more important part, really. Not exactly where these come from, though that's important, but how do we use them for these types of problems? Okay, so again, when we're approaching an integration problem, we're thinking through all different kinds of strategies. If I try to use just u substitution here, and I let u equal 4 minus x squared, I'm going to have an issue because I'm going to have an x with that derivative that I can't deal with. If I try to, I can't just reverse the chain rule here, so we're sort of running out of options in terms of what we have learned so far. What I do notice anytime I see a square root is that kind of sets off a little alarm in my head. This kind of looks like arc sine, so I'm going to make a little note to myself, arc sine question mark. If this is arc sine, what I want to do is I want to think about which is the u part and which is the a part. So in this case, if this was arc sine, the u part would be just x, and the a part would be 2. So I could really rewrite this integral as the integral of 1 over the square root of 2 squared minus x squared. Now that this is set up in a way that I know I can go back, this is going to be arc sine of u over a. So this is going to give me arc sine, or you can write it as inverse sine, of u over a. U is x, a is 2, plus c. And the reason I don't have to deal with anything more complicated is that the numerator is a 1. So this is just arc sine. The only difference is having that 2 in that a spot. All right, let's go ahead and look at number 2. Number 2, when I see it, I say to myself, is this arctangent? Could it be? If it was arctangent, then my u would be 2x and my a would be 5. So I could rewrite this one as the integral of 1 over 2x squared plus 5 squared. And rewriting it that way, at least in the beginning, just kind of makes it easier to think about how we work through this. So something to notice here, if I take the derivative of u, I would get that du is 2 dx. And what that means is I need a 2 to be in this numerator. And I can't just put a 2 in the numerator because I feel like it. I need to also put a 1/2 in front of this integral. So now this inside of the integral, the integrand, is actually just arctangent. So let's deal with that part first. This is going to be arctangent of 2x over 5. I'm not going to forget my plus c. I also am going to have this 1/2 that's in front. And if you think back to arctangent, I also need to multiply by 1 over a, right? I have this 1 over a in the front that I also need to multiply by. So times 1/5. So I'm going to just erase. That's going to become 1/10 of arctangent of 2x over 5 plus c. Why don't you go ahead and pause the video and see if you can work through number 3 on your own. So this looks a bit like arctangent. U would be 2x, not du. A would be the square root of 3. I'm going to take the 8 out. So this is really 8 times the integral of 1 over the square root of 3 squared plus 2x squared. Now I'm going to look at u. If I take the derivative of u, if I take the derivative of that inside function, I would get 2. So I need a 2 here, which means I need a 1/2 out here. So that's going to give me 4 times 1 over a, and 1 over a is going to be 1 over root 3. So let's actually just rewrite that as 4 over root 3 times arctan of 2x over the square root of 3 plus c. All right, number 4. It kind of looks like this might be arc sine, but I'm going to manipulate this a little bit and see what happens when I do that. And I don't have a lot of space, so I'm not going to write my little arc sine question mark. I'm just going to try and use this space as best as I can. U, in this case, is e to the x. A, in this case, is 1. The number on the top is 1, so that's pretty nice for us. So if I rewrote this, I could rewrite this as the integral of 1 over the square root of e to the x squared minus 1 squared. So if I use u substitution here, because right now, the problem with trying to jump right into arc sine or something along those lines is that the derivative of u would be e to the x, and I can't just throw e to the x in the numerator here, because if I did that, I now have x's. I can't multiply by 1 over e to the x. This is not a scalar. I can't change this by a scalar by putting e to the x in the numerator, so I can't do that. So I have to look at what else I can do. Well, let's try and actually use u substitution here. We already said that e to the x is u, so let's change this to be u squared minus 1 squared. And if we do that, du is e to the x dx, which means that du over e to the x equals dx. So this would become du over e to the x. But wait a minute, e to the x is just u. So I could put a u here. So let's rewrite this integral. I have erased it enough times. Now it's probably hard to see. I'm going to have a u. I'm going to have a square root of u squared minus 1 du. So this doesn't really look like arc sine anymore. This looks like, with this extra u in front, this looks like arc secant, which is exactly what it is. So if I go back over here, the one we didn't really talk about, arc secant, has that u in front in the denominator. So this is going to give us arc secant of our u, which is e to the x, over our a, which is 1, plus c. And we need to make sure that we include absolute value. So I'm going to go back. The absolute value of u over a. So one thing I want you to see, e to the x is always going to be positive anyway, so the absolute value is definitely not necessary here, but it doesn't hurt for you to have that. And the a was 1, so this is really just going to be arc secant, absolute value, e to the x plus c. All right, number 6. So right now I just see a polynomial in a denominator. I see that I have something squared, but in the way that it's written right now, u substitution is not going to help me. I don't have a whole lot of strategies that are going to help me. So my gut is, could I make this polynomial in the denominator look like some squares? And I sure could. I could complete the square in the denominator. So that would give me x minus 2 quantity squared over, if I had 7, I would need that to be 4. So this is going to be plus 3. I'm not going to review how to complete the square from Algebra 1. If you need to show more work for that, please go for it. But I'm not going to talk about that right now. So now this does kind of look like something, maybe arctangent. And maybe it would look more like arctangent if I rewrote this as the square root of 3 squared, because now I have the sum of 2 squares in the denominator. So the numerator is 1, the derivative of this piece is 1, so I don't have any weird things happening with a or with u prime. So this is arctan, so this is going to be arctan, and actually I'm going to write it, I haven't written it as inverse tangent like this yet, of x minus 2 over the square root of 3 plus c, and I need to make sure I don't forget my 1 over a in front. Please do not spend time rationalizing your denominators. Leave them irrational. Okay, number 6. My gut on this problem would not to be anything about arcsine or arctangent or anything. My gut would just be, okay, let's use u substitution. Let's let u equal sine of x, so du would be cosine of x dx, which would mean, I'm going to come back and deal with the bounds in a minute, that I would have cosine of x over 1 plus u squared times du over cosine of x. So these cosine of x's are going to divide out. I need to adjust my bounds. If u is equal to sine of x, sine of 0 is 0. Sine of pi over 2 is 1. I actually like those bounds a lot better, 0 and 1 versus 0 and pi over 2. So I have the integral from 0 to 1 of 1 over 1 plus u squared du. Well, now this does look like arctangent. So this is going to be arctangent of u, evaluated from 0 to 1, which is going to be pi over 4 minus 0, which is just going to be pi over 4. Why don't you go ahead and pause the video, work through 7 and 8. Remember all the things that you have learned about integration. Don't just think about inverse trig, but think about all the things that we have learned, pick a good approach, and work through the problem. So on 7, I see rational expressions, so I'm going to divide first. That's going to make this first part of my integral work out nicely. X squared, over 2 minus the integral of x over x squared plus 1 dx. I'm going to use u substitution to solve this part, so I'm going to erase my long division. Out of space here. I'm going to let u equal x squared plus 1, which means that du is 2x dx, which means this integral is going to become minus the integral of 1x over u times du over 2x. So I still have x squared over x squared minus 2, x squared over 2 minus this integral that I just found, which is going to leave me with x squared over 2 minus 1/2 natural log of what was u? It was x squared plus 1 plus c. So no arc trig, even though it kind of looks like we could have some inverse trig happening here based on that denominator, not based on what the numerator is. So on 8, the first thing I'm going to do is split my integral. Then I'm going to use u substitution on the first integral. I'm going to let u equal 4 minus x squared and work through that. So that's going to give you negative 1/2 times u to the negative 1/2, and you can just integrate that using the power rule and then directly substitute back in your 4 minus x squared for u. The second integral that's here is basically exactly the same problem as number 1, except there's a 2. So I could just factor the 2 out. 4 minus x squared dx. And then to save myself the time, I can see looking at number 1, now it's exactly the same except there's a 2 in front. And then I'm going to have arc sine of x over 2 plus c. So the key points in this section, don't forget all the things that you've learned about integration up to this point. All of those techniques are still valid, and you should still think through a problem before you start integrating. But just be aware of these special trig functions that could be occurring based on what you're seeing within the integral. Think about how to manipulate them to get them into the form that you need them to be in. Looking forward to working on this in class with you. Thanks for listening.